the dynamic field theory is what? So let's hear about it.
Thank you. So yes, so the aim of today is to describe to you a technique. Actually, well, the result of the technique will be discussed tomorrow. But the technique that I want to discuss today is this dynamical mean field theory, which is indeed a method that physicists have developed to study dynamics in high dimension. And this is what I want. And I think it has a lot of potential for several of the problems that you're interested in. And it's not been used, I mean, it has been used, but I think there is a lot of things to do. So this is what we're going to study today. So just to tell you, I mean, a little bit of history. So dynamical mean field theory was developed, I think, in the way, at least, in which I'm going to discuss, was developed originally by Heim, who is here, I mean, here in Lesuche, and in the context of disorder system, and then some Zipelius in 81, 82, I think. And then it has actually a very important, impact on disorder system. Then there have been several works still in disorder system. Then there have been work, I mean, by many people, but so there have been a series of work by Giulio and Kurchan, the first one in '93, in which here they studied the out of equilibrium dynamics of spin glasses. And then it has actually a parallel life on quantum system. So in quantum system, the good reference, so the first one are Metzner, I think, and Vollard, 89. And then Georges and Cotrier, I think, 1992. So just to tell you that in this case, people developed something which is very, very similar, and that is used in strongly correlated electrons. And is not, so here I would say that people use it to do theory. Here people use it to do theory and then real application. So they just discover new material using dynamical mean field theory. So I hope maybe one day dynamical mean field theory will play the same role in machine learning. Not so sure, but okay, one can dream. But I think in any case there are many applications ahead. All right, so let's start. So what I'm going to study, so pedagogically, in principle, one should, let's say, present the method in a simple case and then generalize. So I will not do this. I will go directly for something which is complicated, but I think is more useful to you. And all right, so I'm going to study a problem that you have already seen several times, in which you have a loss function. And then you have data, and then you have, let's say, a particular vector, W star, and then here you have these degrees of freedom, which are W. The xi mu are random variable, which are mean 0 and variance 1 over n. The W can be on the sphere or not. Let's say, let's put it on the sphere, but I mean, one can do this or the other. And so this case is something that you have already seen, I think, for this function L, for the moment, you can take whatever you want. And so you have, I think, Mark discussed already several cases. So this is what, for example, just to give you an example, is what physicists, there are examples in which people call this teacher-student, in which you have, so you want to retrieve this W star, and you have, so xi mu, this random vector, and mu goes from 1 to m. And the W here, so this is a vector with indices which goes from 1 to big N. And then you have this parameter alpha, which is m divided by n. So this is a notation that have been used already by Mark, and I think myself when I discussed the Wishart matrices. Okay, just to give you an example, so this is a case, depending on the L that you take, is the case in which you have indeed what you call a teacher, and then a student that has to learn. Or you can also consider other case, like, for example, phase retrieval. This is another example. This is just to give you an example, in which you have, so the loss function will be something like sum over mu of, for example, xi mu dot W star squared square minus psi mu dot w square. I mean, just to give you an example, okay? So these are the kinds of things that you could like to study, you may want to study. And so what we want to study is, well, what happens if you start from a random initial condition? So the initial condition for the problem is random. So it means it's a random W with this constraint. So W is random on the sphere. And we are going to study gradient flow. Now, if you ask me, can we study something else? I don't know, gradient descent, etc. The answer is yes. But it's not, I mean, for the moment, I will just do gradient flow for simplicity. Okay, I will put this lambda to fix that the W should be on the sphere. Again, well, we can also get rid of this and get rid of the lambda. Okay, so this is the problem that we want to study. And now the difficulty, and this is what, well, physicists has to cope with when they study spin glass model, is that, well, if you take n, which go to infinity, so you are in high dimension, so this is, I mean, it's this vector go to infinity, so I mean, it's, and you would like to have something that you can treat. And so the idea is that, in a sense, what you want to do is like when you do mean field theory, is that you want to find an order parameter that has a simple self-consistent equation and that is going to describe the entire process. So this is what we are going to do. And maybe just, again, to put reference. So what I'm going to do is I'm going to use a technique which is called the dynamical cavity method. And, well, this also has a long history. Not sure who started first. Maybe it's in the, I mean, I saw it in the book by Mesar and Parisi and Virazzaro. In any case, the version that I'm going to describe it now, because is the one that was developed in the paper by Goritsas, Urbani, and Zamponi in 2018. And actually, there is another paper in which I think we understood a little bit better. And this is really the things that I'm going to follow. But it's something that you really don't care, really, because it's not at all about machine learning. It's more about R-sphere in infinite dimension. So when you take a collection of R-sphere, so interacting particle model, you take in very large dimension, you can solve exactly the dynamics. And so it's a problem which actually is more complicated than the one that I'm going to describe. And so we had to understand better really how to do the dynamical cavity method and dynamical mean field theory. All right. I think it's all I want to say for the beginning. All right, so what should we do? So, well, the first thing is, so here you have the dynamics here of this vector, which is a vector in n dimension. But actually, there are, in this n-dimensional space, there are just three directions which are really relevant statistically, right? So there is, I would say, one is, if you consider one of the direction of the xi mu. So let's say three type of directions, let's say. Directions are important. So one is you take, let's say, a fixed direction or a direction which is uncorrelated with xi mu. Fixed direction. Maybe let me explain better what I mean. So what I mean is that, well, I take, let's say, one direction, and then I take all the xi mu. So it means that this direction is, well, is fixed. It is uncorrelated with the xi mu, which means that, you know, when you are in n-dimensional space, typically this direction has 0, is almost orthogonal to each one of the xi mu. And let's call it, so for example, and then I can study, so the projection of W over this direction, let's call it Vi, and this will be Wi. Then there is another kind of direction which are important, which are the xi mu. So these are special. So if I look W in the direction of one of the xi mu, this is special because I have it here in the loss here. So we will see these are another kind of important direction. So if I look W in the direction of the xi mu, which is xi mu divided by the norm of xi mu, actually the norm of xi mu, since I define in this way, it's concentrate to 1, so it's just W xi mu, and I will denote it like W mu. And then there is the third direction which is important, which is when you project W over W star. And actually, in this case, you will want to normalize by square root of n. And the reason is that, so in this high dimensional space, so you have this W star, which is here, and you want to know really whether, so in the way in which I normalize, the W typically are of order 1 on any possible direction. So Wi is of order 1. And what you want to know is instead if W in the direction of W star, it really has an important overlap. So if it's like this. So in this way, I have to normalize by square root of n. And this we call the magnetization. Well, M just comes from physics. I will call it M because traditionally it's been called M. Okay? These are the three kinds of direction which are important. And now, what I'm going to show you is that you can actually write simply some set consistent stochastic equation in these three directions. And this is what dynamic and mean field theory is. Questions on the project? Yeah.
Is it already obvious why this kind of directions are important? I mean, I understand number 2 because it comes from data. Is number 1 like, let's say, lap frame that I can think of it? Like,
Sorry, number 1 is?
like a lap frame, I can think of it? Or like why this direction?
So maybe it's my notation fixed is not correct. What I mean is that I take one direction which is uncorrelated with xi mu. So let's say that this is what I meant. So I fix it at the beginning and then I draw the xi mu. And so, so it's uncorrelated with xi mu. This is what I meant. Sorry? Sorry, I didn't understand the... lab frame, yes, lab frame, sorry. Yeah, lab frame is good. And then M, of course, because I'm interested in it. Okay, so the derivation that I'm going to do, even though I decide to do, let's say, a complicated case for the MFT, I will simplify a little bit. So I will consider the case in which is simpler, in which actually I will get rid of this. I mean, I know that this is a stupid case in a sense, but this is just to show you, I mean, how the technique works. And then, I mean, it's a very simple change to add back the what we call the teacher or the xi mu dot v star. So we will just see. I just want to show you how the method works and to avoid and to keep everything in 1.5 hours. I will do it like this. But then I will tell you what is the generalization in the case in which I put back the W star. So in this case, in which I write it in this way, we have just these two directions which are important and not this one. And then this again. I will put it back later. Okay. Okay, so let's write the equation, the gradient flow on, let's say, on a fixed direction, on the lab frame for Wi. So this is going to be, well, it's simple, dWi dt minus equal to minus sum over mu from 1 to big M, L prime, which is just the derivative of this function of psi mu dot W, and then I have psi mu. Okay, I will put it here, the index, psi mu I. And then I have minus, if I put the spherical constraint, I will have minus lambda Wi, okay? And then, well, then I have, let's say, so this is one of the component, so in this lab frame, so I have this direction, which is the direction I. And then I can always write W, I can always write like Wi plus W orthogonal. And I hope you understand what I mean by this. So I split W along the, let's say, a vector which is in the direction I and all the rest. Yes?
Psi mu I is the projection of psi mu on the I.
Exactly. Yes. Thank you. Yes. again, please.
Cycle loss is psi mu dot wi.
So what there is here is, okay, let me be precise. This is, well, it's a scalar product, so you can write it this way, C mu I, wi. Yes?
And this wi is different from the index wi in the sum, right?
This wi, no, is the same? No, it's y.
Okay.
So you mean it's different from what?
So from here we use the...
No, it's the same. I'm just looking at it. Okay. Do you understand the notation? It's clear for everybody. So I split the vector in the two. So now I write the equation for the rest, which is d w orthogonal dt equal to minus sum over mu from 1 to m of L prime psi mu w xi mu orthogonal minus lambda w orthogonal.
I'm confused again. Wi, isn't it a scalar?
Yes. Okay, yes, you're right. Okay, okay. Wi, bi plus w orthogonal. So this is a vector, so I will do like a physicist. So that's clear for you, okay? But now I will not put the vector anymore. Otherwise, all the mathematicians will look weird in a weird way to me. Okay, all right, so now you have these two equations. So what you should do, so if you remember for the physicist, the course that you had in physics, for example, when you derive the Langevin equation starting from Newton equation, or in general, if you are interested in the dynamics of 1 degree of freedom, which is coupled to many others, what you should do, in principle, if you are able to, is that you have your degrees of freedom, which you are interested in. So you should solve the equation for all the rest with Wi fixed. So get W orthogonal as a function of Wi, put it back, and then you have a closed equation on Wi. Then problem solved, in principle. So this is how you do, for example, how you get Langevin equation from Newton equation. So you get 1 degree of freedom, you solve the environment at fixed Wi, you put it back, and you get one equation on Wi, which is a Langevin equation starting from Newton equation. So this is what we are going to do. Again, if you have questions on notation and everything, please.
So you have actually d of those fixed directions vi?
No, it's just one. For the moment, it's just one. So I fix one. So you're right. In principle,
All I is the same.
For all i's will be the same, yes. But for the moment, so in principle, I think the idea is you fix a direction, and then you take, let's say, the infinite dimensional limit, and you look at the equation in this fixed direction. So you're right that I could have taken, many possible directions, indeed.
Can I also just ask why there is prime with L? Because this is like loss function, right?
So because I took the derivative, so this.
Okay, yeah.
Okay.
W star is still implicit in that loss function, right?
No, so I'm deriving, I'm doing the case in which I'm not putting the W star just for simplicity, because otherwise all the equations are bigger, and then I will tell you at the end what happens if I put a W star. Okay. All right, so what should we do? So there is one thing that you should now think about, which is the thing that is going to help us. What is xi mu dot W? So xi mu dot W, you can write it as xi mu orthogonal, scalar product with W orthogonal, plus xi mu I, Wi. Okay, just split into the scalar product. Now, how this scale? So xi mu dot W, well, I use, so xi mu, remember, this is a vector which has, so xi mu I is a Gaussian variable, 1 over n. So this means that xi mu I is over the square root of n. W is a vector on the sphere of radius square root of n. So you can check just using, central limit theory, or this scales of order 1 when n go to infinity, which is normal because, otherwise this would be the function, it has an argument which is weird. So we all take the scaling in such a way that this is of order 1. However, this term here, well, xi mu I, it's of order 1 of square root of n. Wi, it's of order 1. So this one is of order 1 of square root of n. And this is the key to, the dynamical cavity method. Because you see now that the program that I want to do, which is solving for W orthogonal for a fixed Wi, and then put it back, can be done easily, can be done in perturbation theory. Because this is just a small perturbation compared to the solution where I put this to 0, okay? You understand the idea? Now we're going to do it. So the idea is really, well, I want to solve this, put it back. In principle, it's complicated, but in this case, it's not complicated because, I mean, the W orthogonal is a function of Wi. We can get it in perturbation theory. And even better, we will see that we just have to go to linear order in perturbation theory because all the rest in the limit n going to infinity is not important. Okay.
Number of patterns M also tend to infinity, then you can't do that, right?
Sorry, say it again.
If the number of patterns M, they also go to infinity.
So they go to infinity such that m divided by n is fixed. So it's indeed, if there was a different scaling, then I should think about. But yeah, in this case, it's m over n is fixed.
Why can you call this metal main field?
You will see. It's, for the moment, it's not clear, but you will see. It will appear. It's like, you will see, we get something like m equal hyperbolic tangent of m, just slightly more complicated. All right. Okay, so the idea now is, well, we can solve in principle. So we have two equations. So we have, first thing, we can solve the equation on this one, put into 0. So really, I mean, the 0 order of perturbation theory. So we are going to solve the equation. This we'll call it 0, which is minus sum over mu L prime of psi mu dot w. This will be orthogonal 0. And then we have psi mu orthogonal. And then we have minus lambda w orthogonal 0. So this will be solved with the initial condition, which are random on w orthogonal. So this is just, this lives in a space which is n minus 1 dimensional. And well, there is a solution. So in principle, we say, okay, we solve this. Okay, I'm not solving this, but there is a solution of this. And the solution is w orthogonal 0. And then, well, if we have this term here is a small perturbation. So imagine that I add a term here, which I would call h mu of t. It's just a field that I put just for practical purposes. And then I can write the perturbation theory like w orthogonal of t will be equal to w orthogonal of 0 of t plus the integral over dt prime of the derivative of w orthogonal 0 of t when I put a small field h mu, so here I have a sum over mu, at t prime, and then I put at h equal to 0. And then I write what would be the h. The h is the small perturbation, which is here. So it will be psi mu I t prime, no, sorry, w I of t prime. And then in principle, well, you can go, or you can continue. You can have the second order, the third order, etc. But you will see, I mean, it's we can just stop at this order. So it is just formal. So in principle, this you can get it solving this equation, and this you can get it solving this equation. So it's just formal, but they exist. Okay. Okay. And now, well, what you are going to do is that we do our project. So we take this solution, we plug it back in the equation on Wi.
And use everything inside the...
Sorry?
Actually use everything inside the bracket. H.
H mu, so H mu, I was just saying that this term here, so what I mean is that here I can solve W orthogonal with a given H mu, which is not, sorry, okay, I understand the question, no, okay. What I meant is that I can add just an H mu here, psi mu, orthogonal, okay? The solution W0 corresponds to H equal to 0. And then I can define this kind of response function, which is how much W change if I do a small perturbation on H. So here it's, the solution is for H equal to 0. Okay, so let's take this and plug it back on dWi. And again, if you remember, if you saw it, when you derive the Langevin equation from Newton, it's really the same. Okay, so let's go. So the okay, so we'll have dwi dt. Then there is a first term, so maybe I can, let me rewrite this in this way. So this will be psi mu orthogonal, w orthogonal, plus psi mu I, wi. So now there are two kinds of perturbation. So the first thing is, well, here I can have a first term which corresponds to, which is the term of order 0, in which this one I don't take it, and this one I put the 0 term. This is the 0 order. So it will be minus sum over mu from 1 to m, and then I get L prime of psi mu orthogonal, w orthogonal 0. This is the first term, 0 order. Then I have another term, which is the case in which I consider that the w that I have here actually, well, I should put also the correction to linear order. And so in this case, I'm going to have minus sum over mu from 1 to m. And then I will write in this way, dl prime psi mu d orthogonal, dh mu prime t prime. So here I have to put the sum over mu prime also, and an integral over dt prime. And then I have to put the, the h mu prime, which is there. So it's c mu prime I w I t prime. Do you see what I did? So I'm just, I'm just saying, okay, how much this is going to change with the solution W orthogonal that I have when I put a small field, and then this is in h equal to 0. And then I put the value of the small field, which is the correction to linear order. And here, well, I have to sum over mu prime because I had a sum over mu there, and well, I should change another index. Okay. Okay. And then, well, then I have also the other correction, which is the fact that I can realize that this is small. So we have also to expand to this to. We have to consider this is small, is order 1 of square root of n. And so this is going to give me another term, which is sum over mu from 1 to m of L second, xi mu orthogonal, w orthogonal 0. And then I have xi mu, sorry, there was a xi mu I here that is missing. You didn't tell me. And here I have xi mu I again, wi. And then I have minus lambda wi. And this is, correct to linear order, and then we can go to higher order. So just stare at the equation and tell me if you, if you want that I re-explain something, you can tell me.
Can I just ask a question?
Mm-hmm.
So you start off by telling us there's these two different directions, two kinds of directions there. So is the thing you're going to do, you're going to like take this kind of equation and then write the equations for w dots, like c mu's, like a particular c mu, and w dot a particular uncorrelated one.
Yeah.
And then somehow, because things are linear, everything will only be in terms of its dot products. And that's how you're going to get closed equations for them? Is that how you're...
I'm not sure I understood, but maybe you can re-ask me the question once I finish the procedure. So the idea is really, well, I take, first I start with the w in the direction I will get some equation, and then you will see that when I take the direction mu, actually it's almost the same, but there is an extra term, which, and then, then I will explain how you could have almost guessed from the beginning the form of the equation, but we will do it later. Okay, so here is just to linear order. And remember, so there is something which can look strange, is that in your equation, in principle, you have sum of order 1 and the term which is of order 1 over square root of n. So naively, you would say, okay, take the n going to infinity limit, the term of order 1 over square root of n, I will throw it away because it's not important. Now the thing is, not quite, because you will see, even if it's of order 1 over square root of n, it can give you a term at the end which is of order 1. Which is known from what, if you know spin glasses, this would be the Onzaga reaction term. Okay, so now let's look at the difference term in this equation. So there is this term number 1, term number 2, and term number 3.
In 3, those are two psi mu i's?
These are two xi mu I. Yes, because there is a xi mu I which come from here and the xi mu I which come from here. Okay. Okay, so first term number one. So the term number one is what in physics, at least in certain, let's say, especially in liquids, people call the random force. I mean, it's not in liquids, actually, in physics. It's if you do Langevin equation from Newton, the term number one is the random force. So let's call it, let's take the notation this way, F. I will call Fi of t is minus some mu from 1 to m of L prime xi mu orthogonal, W orthogonal, 0, xi mu I. Okay, so let's look at what is this function. So xi mu I is actually uncorrelated with W orthogonal 0 and with xi mu orthogonal. Okay, because I solve, I mean, with this is just xi mu over another other component, so they are uncorrelated. And W orthogonal is solved, and in the equation on W orthogonal 0, there is just xi mu orthogonal, there is not xi mu I. So this process is uncorrelated from this variable. So now what do you have? So if you fix this one, well, what you have is sum over m random variable, which are Gaussian, m and m go to infinity. So you expect that this is a Gaussian variable. And actually, since it depends on t, it will be actually a Gaussian function. And with Gaussian, you always have to compute the mean and the variance. So the mean is 0. So the average of Fi of t is going to be 0. And the variance or covariance is Fit prime. And then, well, so the xi mu I, when I take the covariance, I have the sum over mu and sum over mu prime. But these are independent for if mu is different from mu prime. So I'm going to get sum over mu from 1 to m of xi mu I square L prime xi mu orthogonal, W orthogonal 0 at time t, and then L prime xi mu orthogonal W0 orthogonal t prime. And then I should take the average. When I take the average, this one will become 1 over n. So let's replace it by 1 over n here. And and then this, in principle, this you have a sum over mu which go from 1 to m of this term, and then this, you can show that it will concentrate to the average. Now it's the average over this process. So it's the average over sum over mu of 1 over n of L prime. Well, let me write this again this way. And now since all the mu are equivalent, so I have m times the same thing, and so I have m divided by n, which is alpha, and then I have the average over one of the mu, which is L prime psi mu orthogonal. This is one of the mu, W orthogonal 0 t, L prime xi mu orthogonal W orthogonal 0 t prime. Okay. This is the average over the process, which is psi of W orthogonal, and then there's psi mu orthogonal. Okay. Do you agree? Or it was? And now there is a. Hi, you can come.
I'm orthogonal?
Yeah, you're orthogonal, and also I cited you at the beginning, but you're still there, so you see. It's
Oh, okay. That's terrifying.
all right, so here now you do a trick. I mean, it's not a trick, but it's something which is useful. So now remember, so here in this case, what I can do is that I can just erase this. Now you can shout at me if you want, but I can do it because actually here is safe. So I mean, you remember, you will see why it's not safe later. But here, if I just put the other term, well, this is just the average of L prime, and if I put a correction which is 1 of square root of n, it would be really a correction of 1 of square root of n. So there is no, there is no danger. Okay, so here I can do it, and so what I wrote before is equal to this plus order of 1 of square root of n. So just don't care. Okay? But we can do it here, we cannot do it before. So now this term here, so we have that the first term, here it's a random force. It's a random Gaussian function, f alpha of t, and this random Gaussian function, so it's going to be, so as a covariance, let me rewrite. Can I erase here? Yes, sure. It's equal to something that I will call m tt prime, and mtt prime is just the...
There, the average is over W now, right? In there, the average is over W.
It's W now, yeah. It's W mu, W mu. This is, okay, yes, W. Yes, it's W and C mu, yeah. Okay, so that's the first important part. You see that the, on DWI, so we have a random term, which is a random noise. Okay, so now we go and we look at the other two terms. So term number 2. Okay, I will write it here again. So. Okay, so term number 2, I will just rewrite it. It's sum over mu from 1 to m, and then I have the integral over dt prime of dl prime psi mu orthogonal h mu prime t prime. There is another sum here of our mu prime, and then stay with me m, because I have many indices, and I'm always very bad with indices, so mu prime I, wi t prime. Okay, so this is number 2. Now, in this term, and here you will see why actually we couldn't forget the perturbation to linear order. Look at the term mu equal to mu prime. So now for the moment, let's do just one term in this sum, which is mu equal to mu prime. So this term, so mu equal to mu prime, is going to give us sum over mu from 1 to m, integral over dt prime of dl prime psi mu w orthogonal, this was 0 actually, h mu of t prime, and then here I'm going to get psi mu I square wi of t prime. So what you see is that now I have a sum over m term, and m go to infinity, and I have, well, this term here, which is a square. So this term, and see, this is a square, and it's of order 1 over n. So this is going actually to concentrate and to give me a term which is of order 1. So even though at the beginning you could have think, oh, 1 over square root of n, we don't care. Actually, there is a kind of, I don't know how, constructive interference that gives you that the term mu equal to mu prime, you have to keep it. And so this is going to concentrate and going to go to, okay, minus the integral over dt prime. And, okay, I do it exactly like before. So when it concentrates, I have a sum over, so this one will become a, this one will become a 1 over n. I have a sum over mu, so I'm going to get a minus. I'm writing, and then you tell me if you agree, and otherwise I will put more delta TL prime, and then I have an average, which is del prime psi mu w orthogonal 0 dh mu t prime h equals 0, and then I have the average here. And then I have wi t prime. And as before, here, because this I have just one term, I'm allowed, so here there was an orthogonal, I'm allowed to do this. Okay? So now this function here, I will call it RTT prime, because in physics is what we would call a response function. And so we have that the second term is equal to minus alpha, the integral over dt prime of RTT prime of wi t prime. So we got, the first term was a random force, a random, or a noise with a certain covariance. And the second term is a kind of, well, if you are in physics, you would call it dissipation or friction, retarded friction, which has this form. Well, maybe I can put also the bound in the integral. So the integral goes from 0 to t, because this function actually is 0 if t prime is larger than t, because clearly you cannot change the solution at time t if you put a field in the future that is not going to change. Okay? Questions? Okay. So now there is the third term, which is the easier one. Okay, third term that I should find in my notes. So the third term was minus sum over mu from 1 to m of L second psi mu orthogonal W orthogonal 0, and then we had psi mu I square W I t, and now you have understood how it works. So this is going to go to minus alpha, the average over L second of psi mu W Wi t, which we can rewrite if we call, sorry, this is an average here. If we call this, well, in some way, let's say nu of t, this will be equal to minus alpha nu of t, Wi of t.
Giulio, before you're
Yep.
do you mind explaining again this business of dropping the indices? So you have a W, so for example, you have a W orthogonal 0, and then there you drop that.
It's just because I'm looking at what is the difference between this and this. The difference of order 1 of square root of n. And I say that at the beginning, one should be careful with the 1 of square root of n, which is true because you see that here it gives you a term that you have to consider. But once you are here, so once you are at this stage, here is safe to do it because you see, I mean, you can check, but it's safe. I mean, it's if you put this or you put this, well, it will be just a correction of order 1 of square root of n.
You're approximating.
Yeah. And sorry, something that I didn't say that probably was maybe clear is that here I consider just a contribution mu equal to mu1. If you consider a contribution mu different from mu1, then you can show that this is really a correction. So this is why I didn't consider. It's just the mu equal to mu1, which is the important one. And this one is what in physics is called indeed the Onsager reaction term, at least in when you derive the top equation. And that's it. So now there are no other, if you go to second order, there will be just correction. So now we have, if I summarize, we have the equation on Wi, and I will write it here. And the equation on Wi is kind of cute, is dWi dt, which is equal to minus alpha integral between 0 and t of RTT prime, Wi of t prime, plus f I of t, minus lambda of t, plus alpha nu of t, Wi of t. And then, so this is a stochastic equation. Wi in 0 is just, it's just a random Gaussian variable. And so an f of I of t, you remember it's a Gaussian force, which is equal to m of tt prime, where m of tt prime and r, were defined before. So r is this one, and m was, what's the other expression that you have. So if you look at this expression, this is nice, because it's, what is it? It's what I think people call the Ornstein-Uhlenbeck process, at least with some memory. So what you have is that, in physics, you know that, what you have is that this degree of freedom is subjected to random noise. with a certain covariance, and then some dissipation, which is a kind that is, let's say, is the generalized non-Joven equation. And then there is this term here, which is a kind of, let's say, renormalization of interaction that you have. Okay, it's simple. It's a simple equation, and it's the typical equation that you would get in a system when you take a degree of freedom, you trace out the environment. If you think that the interaction with the environment is not too complicated, you would end up with an equation like this. Okay. Now the problem is not solved, even though this equation is simple. It's not solved because I don't know what M and R are. So if you want to get M and R are, you see that what I should get here, I should get the equation for the evolution of W in the direction mu. So this is the equation that we need. We need the equation on W in the direction mu. And if you have this other equation, then the problem is solved. Questions?
So I'm just
Yeah.
wondering whether this appearance of the plus alpha nu, whether it's really, similar role as what Andrea was saying with this regularization that popped up because of the noise. If here it kind of popped up because of the average over the disorder as well. Is it a similar kind of origin term?
I don't know. I don't know, Andrea, what you think. It's true that it's...
The renormalization of what?
This when you add the alpha nu to the regularization, and that alpha nu that came from the second derivative of the loss that was multiplied by the empirical covariance.
This,
The term is there
so-
because we have finite probability.
so maybe it's, I don't know whether it's like, because it's different from, I think, Andrea, in the sense this is a renormalization due to the interaction with the other degree, the other W, the other degree of freedom. So it's not due to the noise, it's more due to the fact that there are other degrees of freedom coupled with it. But it's renormalized the regularization indeed.
Yeah, but at the fixed point you pass to recover, so you can identify that lambda star with one combination of things. Now I don't remember which one it is,
But yeah, but I mean, in his case it was a linear problem. So here is so it really comes with the fact that one W interact with all the other ones.
but you could take as quadratic, right?
Yeah, if you take quadratic, yes, but in the general case, it's really due. It's like if you have, I don't know, if you have let's say, a simple well which is coupled to harmonic oscillator, you integrate out the oscillator, and then the well, I mean the spring constant of the well is going to change. It's as simple as that. It's just a shift, yeah. You have it again if you. Just to give an example, when you derive the Langevin equation, I mean, it's really the fact that there is a renormalization of, let's say, well, I would say the spring constant, or when you integrate out the other degrees of freedom. But maybe one can think indeed in terms which are a little bit less physics-like and more ML-like. Okay, so let's write the equation for in the direction W mu, in one of the direction W mu, because we need it to solve the problem. So what is the equation for W mu? So let's write it. So we have dW mu dt equal to minus sum over mu prime from 1 to m, L prime of xi mu prime W. That we can always, well, okay, and then we have minus lambda W mu. Now, what I can do an innocent thing. So this sum, I can take out the term which corresponds to mu. So I'm going to write this like minus sum over mu prime different from mu, from 1 to m, of L prime, sorry, there is a xi mu here, mu prime, that is missing, right? So I should write it well. So this is not well written. This is xi mu prime, and then I project it on xi mu. In principle, it will be xi mu divided by the norm, but the norm is 1. Do you agree? So I'm projecting on xi mu. It's fine? Yes? No? Yeah? Is it okay or not?
Can you
Okay.
say what we're calculating now?
Sorry?
What we are calculating now? Can you
So what we are doing now is I want to find the equation in the second kind of direction, the one which are in the direction psi mu. So this W mu, remember, is this W mu that I have here is W dot psi mu divided by the norm of psi mu, but the norm is 1, so I just forget the norm. And okay, so now we divide this sum in two pieces. So there is psi mu prime psi mu, minus, and then there is the part which is minus lambda W mu, and then I have the term which is minus just one term, which is lambda prime psi mu W psi mu square, and that's it. Okay? And now, well, psi mu square, you don't tell me, no, it's fine, it's fine. So now we are done, even if maybe it's not clear why we are done. So psi mu square is equal to 1, so I can just forget about it. It's for concentration. And then, well, this term here, what is it? So now, the direction mu, what it is with respect to the mu prime? You can think it's a fixed direction, it's uncorrelated. So this means that this will give me exactly the equation that I have there. But then we have an extra term. So the equation on dW mu is very simple. I will put it here. Is exactly what we have here, but with an extra term. So it's dW mu dt, which is equal to minus L prime W mu. And then we have minus alpha integral between 0 and t of RT prime W mu t prime plus f of mu t minus lambda t plus alpha mu of t W mu of t with the initial condition, which is the Gaussian. And then, well, these are always random force with the same covariance, and this is always the same function r. And let me write on this side remind you what is r, what is nu, and what is m. So m was, what was m? M was alpha. Okay, you will tell me if I'm wrong. L prime psi mu W mu t, L prime W mu t prime, and then R was equal to L W mu t when I put the field H mu at t prime, and then I put H equal to 0. And nu of t was equal to alpha L2 psi mu of t, with W mu of t. And this is over the process of W mu. Is it okay?
Can I ask, so I think, I don't completely see it, that the forces Fi and Fe are also independent of each other. Is that right?
Yeah, they are independent, yes.
So where does that come from? Because somewhere in their formula we have different mu's or...
Well, first, I think so there is one important thing also to think is that I'm not considering the problem in n dimension. I'm really sticking to, let's say, one stochastic process, and then I take the dimension which goes to infinity, which means I consider one direction, I, and one direction, mu, and then I take n going to infinity.
Right.
So I don't want to say that all these ones are true for all mu, and all these ones are true for all I, because you see, if these are true for all I, so it's true in the whole space, and so, it couldn't be, this one couldn't be true.
Just for your fixed direction I and for your fixed direction
Yeah.
the two forces.
Yeah, sorry, yeah.
The alpha is not in the definition of the nu, no?
In the definition of?
The third equation.
Uh,
Because you put it explicitly.
Yes, thank you, yes, yeah. Okay, so now there was a question why this is a dynamical mean field theory, because now these equations are closed.
The
Yeah.
lambdas
What about the lambda? Okay. So the lambda, so I'm not going to write it, but the lambda, you can fix it in this way. So you have this process here, and you know that the lambda of t is to be such that sum over I of wi t squared is equal to n. So if I take the n on this side, you can say that lambda of t should be such that the average of wi squared t is equal to 1. So it means that if you take this stochastic process, you will have to find lambda of t such that the average over this stochastic process of wi squared t is equal to 1. So this is how you fix. And you can write an explicit equation, but it will not do it. So now why this is dynamical mean field theory? So where the mean field theory come from? And I will say before, it's a little bit like m equal to hyperbolic tangent of beta m. Just, well, m is more complicated, okay? So the idea is here that you see, well, look at this process. So if I give you R, and I give you m, and I give you nu, well, this is a well-defined stochastic process that has, I mean, its own dynamics. Now the thing is, well, R and m and nu are average over the same stochastic process, and it's defined here. So it really means that, I mean, this is how you get a self-consistent equation in principle. So the idea is that you have to find m, r, and nu in such a way that if you run this stochastic process and you take the average over it, and you take these three average, then you find the m, r, and nu that you have used to run the stochastic process. And this is like, again, it's like this m hyperbolic tangent of beta m is this, let's say, is this circular, so you can think in this way, given m, given r, given nu, then you run the stochastic process, you get some, let's say, guess for m, r, and nu, and in principle, if you have the solution, this guess should be equal to the one that you have put at the beginning. And I think you can show that there is a unique solution to this, just by causality, but I will not enter into this detail. Okay? So now we have...
Yeah, okay, we showed it.
Yeah. Yes, but I think it's known, it's from physics, because, okay, I will say that rigorously, but since you can construct the solution by causality, I think it's clear that it has to be.
Well, it's like, it's clear if time is discrete. Right?
Yeah,
but
okay.
If time is continuous, it's
Yeah.
like you have to prove that the solution of an ODE is unique. It requires a little argument, right, to prove. You have to prove basically that this recursion is a contraction.
Mm-hmm.
This is one way to. How do you prove that the solution of an ordinary differential equation is unique?
Yeah, okay, I agree. Since I discretize, I think in the discrete case, yes.
It's discrete, then it's trivial.
I agree, yeah.
It's trivial that the difference equation is unique, but
Yeah.
the ordinary differential equation is not unique.
Yeah.
It's not.
Yes. I mean, say,
It's not
yeah.
always unique.
Yes, okay. I mean, saying in a different way, I mean, is there a continuous limit or not? I mean, if there is a continuous limit such that the discrete process converges to it, then, which is what we usually think,
Well,
then
but
it's
you
okay.
see, for instance, an ordinary differential equation doesn't always have a unique solution if the coefficients are not Lipschitz.
Mm-hmm.
If you look at x dot equals square root of x, that's the solution is not unique.
Okay. All right. But did you have doubt that it was unique?
No, I think
Okay. Okay. Now, okay, I agree. But I will tell you, I mean, it's the nice thing, maybe I can tell you now, the nice thing about this DMFT, well, there are several nice things, but let's say one of them that I can tell you now is that indeed this is something that you can prove rigorously. And so this was done, so the rigorous proof. So in the case of spin glasses, which are not much, I mean, are not that different from this one, were done long ago by Benarous and Guillonnet. I think it was in '97 for spin glasses. I think the proof was really quite a tour de force, which we did large deviation of the measure of the stochastic process. And then there is, I think there is a recent proof for this case, I mean, it's, for this kind of case, by Andrea, which is completely different from this one. Okay? So 2022. So, so that's good. So you know also that that you can show in a rigorous way what you have shown, what I've shown to you. Okay, so now I have still half an hour. Okay. All right, so now you can, so now you have a description of the dynamics in the infinite dimensional space. So let me tell you what you can do with it. So the first thing is that you can do is that we, remember we didn't have W star, so you can put it back, W star. I will. So if you put back W star, there are a few things that change, and I will not write all the things that change because, well, you can look at the paper by, so to get the equation on the paper by Francesca. So, and then, Lenka, Florent, and Pier Francesco, so it's, should be, okay. So there are several papers, and I think the first one is in 2020, in which you can find the equation in which you put back the W star. So if you put back the W star, what's going to happen that is you're going to get also an equation which is dm over dt. Now this equation is just deterministic. Again, if you want to look at it, it's just it's a simple equation in which you have dm dt equal to a function of time, which is that you can determine. It's like R and M, and then you have something which depends on M. So it's a deterministic, there is no stochastic part. And then if there is an M, actually in the expression of R and M change a little bit, they also get a dependence on M. So, it's not, it's just to tell you that it's not something that complicate the question too much. You can have them, and so you have a third equation. And now if you have the equation on M, then what you can study in using all these equations, so you can study first, the one thing is you can study, for example, how the loss as a function of time varies. Because how is the loss as a function of time? So this is, I divide by n, or I can divide by m. Okay, let's divide by m, maybe. So this will be minus sum over mu from 1 to m of L of, so it will be psi mu w star psi mu w divided by m. And this will converge to just L psi mu w star w mu of t average over the process of w mu. And so since if you have solved if you have solved the problem, if you have solved the MFT, this you can compute it, numerically in general, because you can solve numerically this equation in general, not analytically. And so you can study how the loss function varies in time. And then you can ask many questions. Is there some intermediate plateau before finding the signal or not? Does it find the signal? Does the loss goes to zero? All these kind of questions you can address. Second, you can study, is how m of t. So you can find is whether you find the signal or not. So recovering the signal, this is another information you can get. You can see whether the system recovered the signal, on which time scale. And then there is a third observable, which is interesting, which is what in physics we call, is the correlation function. It is a bit of the system, which is sum from 1 to n of wit prime. So it's the scalar product of w with itself at two different times. So this again, this is going to converge to wit prime over wi, that you know because you have it there. And so this what is going to tell you here is really, I have w at time t, and this is, it's going to tell me how much actually the system is going to, decorrelate from the configuration that it had at time t. This is something that has been studied a lot in the context of physics of glasses and spin glasses. And it tells you a little bit also, you know things about the dynamics of the system. So you see, you can have a lot of information in this way about the dynamics of the system. So what I would like to do now is to do some remarks, different remarks, and then conclude. So are there first questions on all this? Yeah.
So if I'm not misunderstanding, this is done for fixed T, and I take the large dimensional limit.
Yeah, so this is, exactly. So this is something that I wanted to say. So it's important to remember that here we are working at fixed T, and so n going to infinity first, and then there is a fixed T, which means that we cannot address timescale that diverge with n with this method.
My question was if there was some generalization.
It's, I would say, you can try to compute correction. I don't think it has been done much for now. Sometimes you can guess maybe what the system is going to do on timescale, I don't know, for the log n, for example. But no, I think it's an interesting idea to try to compute correction to get timescale which goes like n to some power. But it's not been done. Other questions? Okay, so maybe we can discuss a little bit about the interpretation of this problem, of what we have found. So first, there is something that, okay, it's okay for everybody, but to me it was, when I saw it the first time, not in this context, but when you go from Newton to Langevin, was strange. So you started with gradient flow, everything was deterministic, and now we end up with a stochastic equation Wi. That's strange, no? A little bit at least. So what's happening here is that we had this problem in which we had, let's say, for example, I can take a really 1 Wi here, for example. This is one direction, which is fixed. And then what happens is that the dynamics of this Wi, because actually it's coupled to all the rest, so this will be the environment, all this one will be the environment, all this other W. So all this other W has an effect on the dynamics of Wi, and this effect is giving a random force and a dissipation term. And this really is in physics, again, for people maybe that are not physicists, is really the rule. So if you consider, I don't know, a molecule in a liquid, or I don't know, a spin in a magnetic material, and you ask, okay, I have the dynamics of these degrees of freedom, what is the effect of all the other ones? Well, you know what the effect is. There is some thermal noise. You know that for example, if I put a particle at its minimum energy because it's coupled to an environment that is moving, it will get random kicks. This is one term. And the other one is dissipation. Well, I don't know, if I throw a ball here in the air, it's not going to go at a fixed speed forever. It's going to go down, and that means this is dissipation. It's the two things that you always have when you have interaction with other degrees of freedom are, let's say, random kicks, let's say, noise, and dissipation. This is why actually I say that at the beginning you could have guessed a little bit the form of the equation, because you could have said, okay, I have my term, let's say even this one. If I look at what is the equation for this, I know that there is one specific term, it's minus L prime, and then there is the rest, which is the interaction with all the other ones. And the interaction with all the other ones, I should be able to replace this by a force plus a dissipation term. So this would be the naive guess that you do that done, just knowing what happens in physics in general. And in physics, in general, this is true, but sometimes, in many cases, the interaction is more complicated than this. This is not just a Gaussian function, and this is not just linear in W, but the effect is there. You always have these two effects, random noise plus dissipation. Okay, so maybe something that I can tell you is that just very quickly is, so these equations are quite complicated because you see here you have a stochastic process to solve, and in the history of spin glasses, there have been cases in which this equation simplifies a lot, and so I will tell you just very quickly what are these cases, since I discussed them a little bit. So which are the spherical spin glasses? In the case of spherical spin glasses, this is why also they have been studied a lot. This equation simplify. They are more easy to solve numerically. And just to, let's consider the simple case, which is one of the, let's say, specific case that I considered last time. So it's what is called the I1 IP, SI1 SIP, and then you have the spherical constraint. So this one, if you can proceed exactly in the same way, and you can say, okay, what is the equation on SI as a function of time? So you do it exactly the same way. You have SI, you have all the other ones. You integrate all the other ones in perturbation theory. And what you get is that you get an equation which is a random force, f of t, plus a term, which is a dissipation term, which is r tt prime c of p minus 2 tt prime, si of t prime minus lambda of t si of t prime. So this is the equivalent of the two terms that we had before. And then the f of t prime average is equal to c of tt prime, which is defined as 1 over n, which is, well, so it's defined like si of t prime. And then r of tt prime is equal to the average of si of t and hi of t prime. And so, well, these are the questions that you get for the p-spin spherical model. And now you can see why these equations are simple. So now the idea is always the same. So you have this stochastic process. From this one, you should get this two-point correlation function. And once you have it, you know C. This is the response function. And then what you have to do is you have to find C and R in such a way that you close the equation. And you see why now is simple. Now why this is much simpler than the other. I mean, it's, again, think that if you know f of t, you know r, you know lambda, I mean, this is a linear equation, right? It's a linear equation with noise, so you can solve it. At least you know the solution. And since you know the solution, then actually you can really close the equation that maybe I will show you tomorrow on C and R. Whereas in the other case, you cannot, because this is a nonlinear dependence on W. So this stochastic equation, you cannot do anything except solve it numerically. So here you get closed equation on C and R, which is why actually this model has been really studied a lot, because it's the numerical way to solve the DMFT equation is much simpler. Okay.
Actually,
Yeah.
so is it true, like for the case of square loss, also you get a linear term in the first version?
So if you, well, yes, if you use, but it wouldn't, so let me see, it wouldn't be the square loss, it's the, yes, if you take really the square loss, yeah, you're right.
It
so.
kind of is thing
Yeah,
because it's
yeah.
a polynomial in that case anyway, like a fourth-order polynomial.
No, so if it's, why it's a fourth order, so if it's a fourth order polynomial, so this should be, if this is linear in W, then it's the same, yes. So if L prime of W mu is A W mu, then it's the same, then you can solve it exactly. Yeah, indeed. Okay, so now I would like to end with several remarks. So what is the pro and cons of this DMFT? So first thing, just to tell you it again, I said already, but first, this is true when n go to infinity first, and t fixed, which means that you cannot get in the time scale which diverge with n. So this is not something which is welcome, but it's something that you get. If you want to go to scale which diverge with n, you either compute corrections or, well, you do something else. Then the other thing is that is very versatile, this method, in the sense that I derive it for gradient flow, okay, but actually you can do, I mean, it's very general. So the first thing is, I mean, if you see, I never use really that, I mean, what kind of equation I had. So I can put, for example, momentum if I want, no problem. I can put, so the It's true for gradient flow. I can put, I don't know, Langevin, which means I can, if you want, I can add noise. So exterior noise, it will be just adding here a noise. So you can, this is it's just trivial. I mean, all this. You can do momentum if you want. I mean, you name it. You can take the dynamic that you want. And if you want, I mean, I did it for continuous variable. You can do it for discrete variable. So if you study, let's say, Monte Carlo problem, and you work with variable which are binary, then you can do it. So there are different people that have studied these things. So for example, studying the effect of acceleration, for example, acceleration using the MFT has been done by Sarao and Urbani. Using, for example, what happens, I mean, not in the concept of machine learning, but just that if you take discrete variables, you can just repeat it. This was done by long ago by Ace, Feller, and Hopper, 94, well, etc. So this is just, well, to tell you indeed that, I mean, you can study many problems that, I mean, you may want to study in machine learning, just changing slightly the equation that I gave to you. And in the recent years, so the MFT has been actually used a lot. And especially, so I mean, it's in by well, I think there are several papers by Francesca, Link and Flaron, and Pier Francesco. They study, well, they use this equation to study, well, for example, phase retrieval, or also, I don't know, what is the effective temperature? This is what Francesca with Pier Francesco, what is the effective temperature? You know that there is this idea that when you do stochastic gradient descent, you have a temperature which is learning rate divided by batch size. So they address this question more from a physics point of view. What is the correct temperature? So this is just to tell you, there are many questions that you can answer. And I think actually that we are just at the beginning of what one could do. And we are just at the beginning, and the reason is that there is a little bottleneck, which is how you solve numerically the MFT, which is a bit complicated. Yes. And so I will end with this. So the numerical solution is what should be improved, I think. So the numerical solution, in principle, is simple, is exactly as I told you. So you start with a guess. You take the discrete version of the equation. You start with a guess for M, R, and U. Then you solve the stochastic process. You get the averages, which correspond to M. So let's say that here it's Mn, or N, U, N. Here you get M at time Mn plus 1, Rn plus 1, and U, N plus 1. And then, well, then what you do is that you say that M nu is going to be equal to 1 minus alpha M old. This is really, you see, it's really a poor man way, probably, to solve it. And then, well, you take an alpha which is small enough, and then you go back, and you hope that it converge. And in many cases, it converge, indeed. So I think it's just to put some reference. I mean, I think in the case of continuous variable, not in this context, but in other contexts, which is actually theoretical ecology, this was first done by my PhD student, Félix Roy. I don't remember when. And then, so indeed, in the context of the perceptron was really done by Francesca. But the fact is, well, it's complicated, but I think it's just a problem of applied math that maybe we should try to work more. And just to tell you, to make a parallel, this in the MFT application of the MFT to quantum problems, the people are really seriously work on how to solve this, let's say, solver to this consistent equation. And now they are able to do incredible things. And they are able to do incredible things and also incredible physics and design new material because they spent a lot of time to improve this solution. And once you have improved the solution, imagine that, I don't know, there is a web page in which you just click and use the MFT. You can now ask many, many questions for at least, for example, simple neural network with a few nodes, and then ask whatever you want. You can also study, for example, the Hessian with this, how the Hessian depends on time, what's going to happen at the solution at long time, All these kinds of questions can be addressed, and I think this is really something which would be, it's important for the future. But this is where we stand now. And I think it's all I wanted to tell you. So tomorrow, I'm going to tell you using this kind of techniques, what we can really say about the dynamics. So I describe the energy landscape that we have, which are full of minima. And so the question that we want to answer is, okay, when you have many, many minima, what the dynamics is going to do, or it's going to find the signal or not? Do you need that trivialization of the landscape, or you can find the signal even in presence of many, many minima? And then if you try to erase the minima, the rough landscape using stochastic gradient descent, do you gain something or not? Okay, but this is all for today. Other questions? Yeah.
So here the psi mu were all uncorrelated, right?
Yes.
And therefore one could write only one equation for the W mu. Would it be a terrible mess if one had a structured?
I think it's a very good question. I mean, it depends how structured they are, but put a bit of structure and write the equation. Indeed, if you had, for example, the xi mu that have a covariance which is, let's say, diagonal, but then there is a particular direction, I think one could do it. But it's not been done, that I know. Other questions? Okay. Good lunch.